In the 19th century, engineers were deeply focused on improving the efficiency of steam engines. They grappled with questions like, how hot should the fire be? What substance should be boiled, water or something else? These practical challenges led to the birth of a new scientific discipline, thermodynamics. Thermodynamics introduced foundational concepts such as heat, temperature, and energy into the scientific lexicon for the first time. Out of this emerged what is arguably the most important law for understanding heat, the evolution of the universe, and the passage of time, the Second Law of Thermodynamics. At the heart of the second law is a revolutionary concept known as entropy. Entropy explains why, when left to natural forces, structures deteriorate, mortar crumbles, glass shatters, and buildings collapse. To grasp this, it's helpful to think of objects not as singular entities but as collections of countless smaller parts, like individual grains in a pile of sand. Entropy measures the number of ways you can rearrange these parts without altering the overall structure. For example, consider a simple pile of sand. There are trillions of ways to shift the grains around without changing its basic form, making it a high-entropy state. Now, if we shape that same sand into a detailed sandcastle, we've introduced order. The number of ways we can rearrange the grains without destroying the castle's form is drastically reduced. This makes the sandcastle a low-entropy structure. If we leave the sandcastle exposed to the elements, wind and weather will inevitably cause it to crumble back into a disordered pile of sand. Fundamentally, nothing in the laws of physics forbids the wind from spontaneously arranging sand into a perfect castle. However, the probability of that happening is astronomically low because there are so few configurations that resemble a castle compared to the countless arrangements that form a simple pile. This statistical reality is why entropy tends to increase. Disordered states are vastly more probable than ordered ones. The second law of thermodynamics, stating that entropy always increases, isn't just about physical structures. It also explains a profound phenomenon, the arrow of time. Time moves in one direction because it aligns with the natural progression from order to disorder, from low entropy to high entropy. Today, this understanding of entropy has implications far beyond steam engines. It helps explain the behavior of complex systems, from the formation of galaxies to the flow of information in quantum computing. The second law remains one of the most powerful principles in all of physics, connecting the microscopic mechanics of particles to the grand evolution of the universe itself.